So in this lesson, we are going to learn how to find the voltage across a capacitor in a circuit. And basically, we are going to look at voltage across series and then parallel capacitors. So in this lesson, we are going to solve two examples. Let's try to solve them one after the other. So for example 1, find the voltage across each capacitor in the circuit below. Now in this circuit, we have a voltage source that is a 30 volt source, and then we have 4 capacitors connected in the circuit. Now we want to find the voltage across each of the capacitors in the circuit. So how do we solve this problem? So like we do for resistive circuits, the first step is basically to find the total resistance. So in this case, we want to find the total capacitance, or what we call the equivalent capacitance. So in the previous lesson, we learned that for capacitors in parallel, for parallel capacitors, assuming we have 2 parallel capacitors, if we want to find their total or their equivalent, then what we do is we basically add them. So that's basically going to be C1 plus C2, assuming we have 2 capacitors in parallel. And then for series capacitors, what we do is basically we are going to say that we have 1 over C1 plus 1 over C2. So basically that is the reciprocal of what we have in the brackets. So basically this is how to find the capacitor combination of 2 capacitors in series. Now we are going to extend this same concept to solve this particular problem. So in that regard, how do we find the equivalent capacitance of this circuit? Now, looking through this terminal, you realize that these 2 capacitors are connected in parallel. So we want to find the parallel combination, and basically for the parallel combination, let's call that CP. So CP parallel means we want to add the 2 capacitors. So that's 40 plus 20, and basically this is 60. Okay, so that's 60 millifarads. So that is the parallel combination of these 2 capacitors. Now the next thing we are going to do is that we need to understand that the parallel combination is going to be in series with these 2 other capacitors. So assuming we want to redraw the circuit, then basically we are going to have something like this. So this one becomes the 20 millifarads, we have 30 millifarads, and then the parallel combination, which is 60 millifarads. So to find the equivalent capacitance, that is basically giving us 1 over 20 plus 1 over 30 plus 1 over 60. Actually, we are going to find the reciprocal of this value. Okay, so all to the power -1, and then when you compute this carefully, you are going to get 10 millifarads. So basically this is the equivalent capacitance of this particular circuit, that's 10 millifarads. Now after finding the equivalent capacitance, what we need to do next is to find the total charge in this circuit. We need to find the total charge. Now to find the total charge, which is Q, is said to be equal to the equivalent capacitance times the source voltage. The equivalent capacitance times the source voltage. Now equivalent capacitance, that is 10 millifarads, and then the source voltage is 30 volts. So when you multiply these 2 values, 10 by 30, we have 300 milli, and then unit for charge is coulomb, so we have 300 millicoulombs. So that is the total charge in the circuit. Again, considering this particular circuit, you realize that here we have the parallel combination replacing these 2 capacitors. So it means that these 3 capacitors are connected in series. So let's call the voltage across 20 millifarads V1, that of 30 millifarads V2, that of 60 millifarads V3. Now what really happens here is that for capacitors in series, the same charge is expressed or seen on each of the capacitors. So it means that the total charge, which is 300 millicoulombs, is the same charge that is seen on the 20 millifarads, 30 millifarads, and then 60 millifarads capacitors. So what really happens here is that the total charge, which is Q, is equal to C1 V1, where C1 is this capacitor, 20 millifarads, and then V1 is the voltage across 20 millifarads capacitor, and that is equal to that of C2 V2 and then C3 V3. The main idea is that for capacitors in series, the same charge is seen on each of the capacitors. The charge is passed on from capacitor to capacitor and to the other capacitors. So in that regard, then we can have an equation for the voltage and try to find the voltage across each of the capacitors here. Then from each of them, we can find the voltage. So for V1, we say that V1 is basically going to be Q divided by C1, that is for the first one, and that is simply the total charge, which is 300 millicoulombs, divided by C1, which is 20 millifarads. So 20 millifarads. So here we have 0 cancels 0, 2 goes into 30 15 times. So we have 15, milli cancels out milli, and then units for voltage is volts, so that's 15 volts. So that is V1. That of V2, we are going to have Q over C2, that's equal to total charge 300 millicoulombs divided by 30 millifarads, that is basically equal to 10 volts, and then we have that of V3, that is equal to Q over C3. So we have 300 millicoulombs divided by 60 millifarads. So this cancels that. Here we have 6 times 5 is 30, so we have 5 volts. So voltage across 20 millifarads is 15 volts, voltage across 30 millifarads 10 volts, and then voltage across 60 millifarads is 5 volts. Now notice that for the original circuit, we didn't have 60 millifarads. This is as a result of the parallel combination of 40 and then 20 millifarads. Now because this is the parallel combination, it means that, you know, for parallel capacitors, the same voltage is expressed across them. So the voltage across the 60 millifarads is going to be the same voltage across 40 millifarads and 20 millifarads. So what this primarily means is that we can conclude that therefore, so we say voltage across 40 millifarads, that is 5 volts. Voltage across 20 millifarads is also 5 volts. So basically these are the voltages across each of the capacitors given in the circuit. Now let's move on to the second example. Also for example 2, we want to find the voltage across each of the capacitors in this circuit. Now in this circuit, we have a 60 volt source, we also have 4 capacitors, and then we want to find the voltage across each of them. So like we did in the previous example, the first thing we are going to do is to find the equivalent capacitance. Now looking into this terminal, you realize that we have these two capacitors connected in series, that is 60 microfarads and then 30 microfarads. They are connected in series. Therefore, for series capacitors, so for the series combination, we have CS, so that is we are going to say, because we have two of them, we basically say that is equal to 60 times 30 divided by 60 plus 30. For the numerator, we have 1800 divided by 90, and then 9 goes here twice, so that becomes 20. Therefore, we have the series combination to be 20 microfarads. That is for 60 and then 30. Now, this 20 microfarads will be in parallel with this 20. So for the parallel combination, we are going to have 20 plus 20, and that's equal to 40 microfarads. Then this 40, which is here, is going to be in series with this 40. So we can call this one CS1 and then CS2. So that is the second series combination. So that is 40 times 40 divided by 40 plus 40. So 4 times 4 is 16. We have 2 zeros. And then 40 plus 40, we have 80. We have basically 80. So 0 cancels out 0. 8 here 1, 8 here twice, and then 0. So basically that is 20. Therefore, we can say that the equivalent capacitance is said to be 20 microfarads. That is the equivalent capacitance of this circuit. So next, we want to find the total charge. So total charge Q is said to be C equivalent times voltage. Now this is basically equal to, we have 20 microfarads times source voltage, which is 60, and basically this is, we have 20 times 60, that is 1200. So 1200 microcoulombs. So this is the total charge in the circuit. Now let's focus on finding the voltage across each of the capacitors. So now at this point, we are going to reduce this particular circuit. So we have the source voltage, don't forget, that is 60 volts source voltage, and then we have this capacitor that is 40 microfarads, and then also notice at this point that for this combination, that is a series combination, we had 20 microfarads, and then we combined that with, in parallel with this 20 microfarads, and then we had 40 microfarads. So we are going to put the 40 here. So this is that 40 microfarads. So in this case, these two are connected in series. That was the calculation we did here. So if you want to find the voltage across each of them, let's call this V1, and then let's call this V40 microfarads. So in that regard, we can say that since we know that they are in series, we know that the total charge Q is said to be C1 V1, and that is also equal to, let's say, in this case, we can call this 40 microfarads. Okay, so 40 microfarads, okay, times the voltage across 40 microfarads. Okay, so don't be confused. This is for that, and then that is also for that. Okay, so focusing on this part, Q equals C1 V1, you can say that V1 is equal to Q over C1. We had Q to be 1200 microcoulomb divided by C1. C1 is 40 microfarads. So 4 goes here once, 4 goes here 3 times, and then 0. So that is 30 volts. So V1 is 30 volts, that is voltage across 40 microfarads. Now we are going to split this. Okay, now even before we split this, from KVL we know that the voltage across this particular capacitor is going to be basically the source voltage, which is 60, minus the voltage across this one. So in effect we have the voltage across this combination capacitor to be 30 volts, also 30 volts. Okay, so V1 is 30, and then voltage across 40 microfarads, this one is also 30 volts. Okay, so we are going to open up this capacitor. So you can do that by drawing something like this. Here we have the positive terminal here, positive, negative, and let's say this is, now this time this is not going to be 40. Okay, this is going to be 20. Okay, this 20 V2, the voltage across C2, so that's 20 microfarads. Okay, and then notice that we first of all combined these two, and that also gave us 20 microfarads, so that's going to be 2020. Okay, so 2020, but notice that this is V2, okay, voltage across C2. So the voltage here is what we had as 30 volts. Okay, so since the two are connected in parallel, it means that the same 30 volts, okay, is expressed across this particular 20 microfarads capacitor. Okay, so here we are able to understand that voltage V2 is equal to 30 volts. Now in that case, let's move on to find the voltage across these two capacitors. Now this time they are connected in series. Okay, they are connected in series, so 60 and then 30. So this time we are going to have them like this. So this is 60 microfarads, 30 microfarads. They are connected in series like this. So, and then the voltage you are going to share is 30 volts. Okay, remember that this is the combination, and the voltage you are going to share is 30 volts. Now, to find the voltage across 60 microfarads, so that is V3, and this is V4. So that is V3 is basically going to be the value of this capacitor. So 30 divided by the sum of the two capacitors, that is 30 plus 60 times the voltage you are going to share. Okay, that is 30 volts. Okay, so in this case we are going to have 30 divided by 90 times 30. Okay, so 0 cancels 0, and then here we have 3 goes here 3 times, and then 3 goes here 10 times. This 3 will cancel, that's 3, and then we are left with 10. So it means that V3 is equal to 10 volts. Okay, voltage across 60 microfarads is 10 volts. And then also for this, because the shared voltage was 30 volts, we can say that then V4 is equal to 30 minus 10, and that is basically 20 volts. Okay, so this is the voltage across the 30 microfarads. Well, you can also say that V4 is equal to the value of this capacitor, which is 60, divided by the sum of the two capacitors, 90, times 30 volts. Okay, so basically we say that 20 goes here, or better still 30 goes here 2 times, 30 goes here 3 times, 3 here once, 3 here, 10, 2 times 10, and basically that is 20. Okay, so basically these are the voltages across each of the capacitors C1 through to C4.